Alright, hey everyone. So today we're going to be talking about complex numbers. So in the past lessons we talked about polynomials with zeros that had real zeros. Today we're going to talk about the other set of numbers, complex numbers, that we haven't yet talked about. But you might remember from algebra 2. Okay, so for you to do now, it's to show that -3 is a lower bound and 5 is an upper bound for this polynomial. And for part B, what are the zeros of this polynomial? Okay, so this is a review problem from, one of last week's topics, upper and lower bounds. And then for part B, we'll segue that into the topic for today, which again is complex numbers. Okay, so if you want to try this on your own, please pause the video now and then we'll review. Okay, so let me scroll up for the solution. Alright, so here it is. So if you remember from the upper and lower bound theorem, we're going to use synthetic division. And to show that an upper bound, we have to have all non-negative numbers, so either positive or 0 in the bottom row. And then for the lower bound, it has to be alternating signs, so like positive, negative, or negative, positive, negative, positive. Okay, here's our polynomial, x to the fourth minus 2x to the third minus 9x squared plus 2x plus 8. Okay, and again, our problem was to show that -3 is a lower bound and 5 is an upper bound. Okay, so -3 is the number here. Again, synthetic division, drop down the 1, multiply, you get -3, add, you get -5, multiply again, you get 15, add that, you get 6, multiply, you get -18, add that, you get 16, sorry, -16, multiply, you get 48, and then add that, you get 56. Okay, so that's for the lower bound. For the upper bound, we'll have, 5 is the number that we want to show for. So drop them the 1, multiply, you get 5, add that, you get 3, multiply, you get 15, add that, you get 6, multiply, you get 30, add that, you get 32, multiply, you get 160, and then add that again, you get 168. So as you can see, it's all non-negative, so therefore it's an upper bound. And yeah, this is a lower bound because, again, this is alternating signs. Okay, so that's part A. For part B, this is a different polynomial. And this question was asking for what are the zeros of this, right? So initially, as we've been doing, right, we're going to first use the rational zeros theorem, right? Plus minus p over q. So in this case, the factors of 1, the constant term, just 1, and the factors of the leading coefficient, also 1, is just 1. So therefore, it's plus minus 1 over 1. So yeah, those are possible rational zeros. And if you plug this in, neither of them are going to work, right? Neither of them are going to be 0. And you can actually tell that without even evaluating. You plug in 1, right? And you're going to get a positive number, right? Because you have x to the fourth, and then, yeah. And then -1, I guess for that you would have to check because this would lead to a negative number. But yeah, you'll see that that does not work either, right? So yeah, let me just confirm that actually. So -1 to the fourth, that'll be positive 1. This will be -2, right? So 1 minus 2 is -1, and then -1 plus this would be 2, right? Because 2 times -1 squared is 2. So we get 1 again, and then 1 plus 1 is 2. But yeah, either way, neither works. And you might be thinking like, since the rational zeros theorem is supposed to lead to all possible rational zeros, then something must be wrong, right? But, as I say here, right, there are zeros that this theorem does not detect, right? Because the rational zeros theorem doesn't detect irrational zeros, right? So, in other words, like zeros that can be written or are written as non-fractions, so zeros that can't be written as fractions. And then, secondly, it doesn't detect complex zeros. So, if there's an imaginary number, right, that is not detected by this rational zeros theorem. Okay, so therefore, this polynomial here is going to have either irrational zeros or complex zeros. Okay, and let me go down to the rest of the notes. Okay, well, actually, let me pause here. If you want to, or if you need to copy this, please pause the video here, otherwise I'll move on to the rest of the notes. Okay, so let me give you an overview of the rest of the lesson. First, again, we're going to talk about imaginary numbers today. That's part 1, and then next we're going to talk about complex numbers. So imaginary numbers, imaginary number I, and then complex numbers. Right, complex numbers being, an expression of the form a plus bi, which involves the imaginary number I. All right, next part is just some rules regarding arithmetic of complex numbers, and then some examples. And then lastly, we'll talk about division of complex numbers and some more follow-up questions. Okay, so let me go to the slide for that first definition. All right, here's the imaginary number I. So the imaginary number I is equal to root -1, square root of -1. And it was originally invented to solve quadratic equations with no real roots. For example, x squared plus 1 equals 0, right? Because if you subtract 1 from both sides, you get x squared equals -1. And then you take the square root, right? And you can even, picture the graph. So x squared plus 1 is going to be above the x-axis, right? So this is going to be like up here, right? So there's not going to be any real x-intercepts, right? So no real zeros. Okay. But yeah, that's how it's defined. I equals square root of -1. And just some follow-up rules regarding the imaginary number I. So I to the 0 is 1. I to the first is just I squared is -1. And that makes sense because you're taking the square of both sides. So you get the square of square root of -1, which is -1. I cubed is -I. And that also makes sense because I squared is -1, as we see here. And then -1 times another I is equal to -I. I to the fourth is equal to 1. And that you could see as I squared times I squared, which is -1 times -1, which is 1. Okay. All right. One thing I should mention is, even though we call it the imaginary number I, so initially the history behind is like the people, like the mathematicians who were working with imaginary numbers. At first, they thought we didn't have any real life application, so that's why they called it imaginary. But as we know today, and as scientific discoveries have been made, right, we see that the imaginary number I actually does come up in practical use. Okay, one example is in physics. If you study circuits in engineering, you probably won't see it in high school. So, if you take a college class in physics, like an engineering class, then you'll see the imaginary I when you study, for example, like circuits. Okay. All right. But anyways, the next example is what is I to the 18th and I to the 33rd. But before I go on, let me just say, if you need the notes here, then please pause the video. But otherwise, I will go over this example. Okay, so let me scroll up for the solution. Okay, so I to the 18th. So the idea behind these problems is we're just going to rewrite everything in terms of I to the 4th, if possible. Okay, so I to the 18th is equal to I to the 4th power, right? Because you remember the laws of exponents. If you take an exponent to a power, then you multiply, right? So it's 4 times 4. So I to the 4th power is equal to I to the 16th, right? 4 times 4. And then we still have 2 left, so we have I squared. Okay, so this I to the 4th times I squared. Now I to the 4th, as we see here, is equal to 1, right? So we're going to replace I to the 4th with 1, and that'll be 1 to the 4th times I squared. So this will be 1 times I squared, and as we see here, I squared is -1. So therefore, the answer to this question is -1. All right, next we have I to the 33rd. I to the 33rd is equal to I to the 4th to the 8th power, right? Because 4 times 8 is 32, and then we have 1 I left over, so we have I to the 32 times I. Now, actually, let me write this in. I to the 4th is 1, right? So we have I to the 8th times I. So therefore, this is equal to I, right? Because 1 to the 8th power is just 1, and then 1 times I is I. Okay, so this answer is I. Okay, so if you need to copy this example, please pause the video here. Otherwise, I'll move on to talking about complex numbers. All right, so complex numbers is something that we've talked about before in this class and also in Algebra 2, but we're going to go through it again just for a recap. Okay, so a complex number is an expression of the form a plus bi, where a and b are real numbers and I squared is -1. The real part of this complex number is a, so this is the real part, a. The imaginary part is b. Okay, just the number b, not bi. It's just the imaginary part is just b. And two complex numbers are equal if and only if, this is pretty obvious, if only if their real parts are equal and their imaginary parts are equal. So it has to be exactly the same, right? So 3 plus 2i, the only thing that it's equal to in the complex number system, right, is 3 plus 2i. So yeah, they have to be exactly the same complex part, same real part and same imaginary part. So a and b have to be the same for them to be equal. All right, let me pause there so you can copy that, or rather pause the video if you need to copy that, and then once you're done, resume the video. Okay, so part 4 is some arithmetic rules regarding complex numbers, and then division, we'll talk about that later. Okay, so for adding and subtracting, we combine the real and imaginary parts separately. Okay, so we have a plus bi plus c plus di. So you add a and c, and then you add b and d. Okay, so this would be a plus c plus b plus di. This will make more sense, or it'll be more clear with actual numbers, but yeah, these are the rules. Okay, a plus bi minus c plus di. It's what you would think it is, so it's a minus c, right, because you distribute the negative, so a minus c, and then for the imaginary part, it's b minus d. Okay, so you just take, just subtract, right? For multiplying, we combine them as binomials, so in other words, we FOIL, right? Okay, so we're going to do, for a plus bi times c plus di, we have a times c plus a times di, which is a di, and then bi times c, which is bci, and then lastly we have bi times di, which is bdi squared. Okay, now bdi squared, as we know, I squared is equal to -1, so we're going to combine this, right? So this is going to become bd times -1. We can combine that with AC. So that'll become AC minus BD. Again, because I squared is -1, so this will become negative BD. Okay, so AC times minus BD, right? Those are both real parts. And then for the imaginary part, we have this. For that, we factor out I, and then we get AD plus BC times I. Okay. All right, if you need those notes, please pause the video here and then resume. Okay, next example. We're going to calculate the following. So we have 6 minus 5i plus 2 plus 3i. So again, it's what you think it is. 6 plus 2 is 8. And then -5 plus 3 is -2. So we have 8 minus 2i. Part B, we have 6 minus 5i minus parentheses 2 plus 3i. So we have 6 minus 2, which is 4. And then -5i minus 3i, which is 4 minus 8i. Part C, we have 6 minus 5i times 2 plus 3i, right? Same complex numbers here. So we get 6 times 2, which is 12. Then 6 times 3i, which is 18i. Then -5i times 2, which is -10i. And then -5i times 3i, which is -15i squared. Okay, -15i squared, right? We can write that as plus 15, right? Because I squared is -1. So this becomes -15 times -1. Actually, I'll write that. Okay, so this again is I squared is -1, right? So yeah, for this part, so this would become 12 plus 15, right? Because negative, so it's going to become positive 27. And then for the imaginary parts, we have 18i minus 10i, which is 8i. Okay, so it would be 27 plus 8i. Okay, so if you need those solutions, pause the video here, and then resume when you're ready. All right, last thing is division of complex numbers, and then just some more practice questions. Then we'll be done. All right, division of complex numbers. For every complex number a plus bi, there is a corresponding number a minus bi called its conjugate. And you might remember the word conjugate from, radicals in algebra 2. Like, for example, if you had the radical 1 plus root 2, the conjugate of 1 plus root 2 would be 1 minus root 2. Likewise, we have a conjugate for complex numbers. Okay, and follow-up question to that is, what do we get when we multiply the two? So if you multiply a number, complex number, by its conjugate, you get a squared plus b squared, right? Because you get a times a is a squared, then a times negative bi, which is negative abi, then a times bi, which is plus abi. So that'll be 0, right, for negative abi plus abi. And then lastly, we have bi times negative bi, which is negative b squared I squared. Okay, so negative b squared I squared. I squared is negative 1, so you get, actually let me write that in. A squared minus abi plus abi minus b squared I squared. Oh, whoops. Sorry, b squared times I squared. Okay. All right, but yeah, so this part sums to 0, right? And then I squared is negative 1, so this entire thing becomes negative b squared times negative 1, which is positive b squared. So all in all, it'll become a squared plus b squared. Okay, so while we use this, the conjugate is especially useful when we divide two complex numbers. So we need it for dividing complex numbers, as we'll see in the next two examples. All right, if you need these notes, pause the video here and then resume once you're ready. Okay, so just some follow-up questions. If you don't know, I should not say 30 minutes. Maybe like 15 or 10 minutes. Let's say 15. All right. Anyways, for the first question, 5 plus 6i divided by 1 minus 3i. So as we said just earlier, right, we're going to multiply by the conjugate. So the conjugate of the denominator is 1 plus 3i. So essentially, we have this division of complex numbers problem, right? It's 5 plus 6i divided by 1 minus 3i. So what you actually do, the operation that this is describing, division of complex numbers, is you have to multiply by the conjugate of the denominator, right? Okay, so that'll get rid of the imaginary number in the denominator. So it's kind of like rationalizing a fraction, right? We don't want a radical in the denominator. All right. Anyways, the numerator is going to become 5 times 1, which is 5. Then we have 5 times 3i, which is 15i. So let me write that in, 15i, and then plus 6i. So that's where we got that 21i. Let me get rid of that. Okay, and then the last part is 6i times 3i, which is 18i squared, okay, which we have here. Okay, so this middle part becomes 21i, which we have here, and then 18i squared is 18 times negative 1, so that becomes negative 18. So 5 minus 18 is negative 13. Okay, so in the numerator we get negative 13 plus 21i. Okay, in the denominator we get 1 minus 3i times the conjugate, 1 plus 3i. So we get 1 times 1, which is 1, then 1 times 3i, which is positive 3i, then negative 3i times 1, which is negative 3i. So that'll be 0. And then negative 3i times 3i is negative 9i squared. Okay, negative 9i squared is positive 9, right? Because I squared is negative 1. So it'll be 1 plus 9, which is 10. Okay, so we get this expression, negative 13 plus 21i divided by 10. And if you write that in a plus bi form, as you'll see on the homework, those are the directions. So just to be consistent with that, we'll have negative 13 over 10 plus 21i over 10. Okay, that's your answer for question 1. All right, next we have question 2, 13 plus 11i divided by 4i. So 13 plus 11i divided by 4i. So technically you could multiply by the conjugate so technically this can be written as 0 plus 4i. So the conjugate would technically be like 0 minus 4i. But you can just multiply by I, because again the goal here is to get rid of the I in the denominator. Okay, so I'm just going to multiply by I. Let me fix that. Okay, yeah, not that mattered, but yeah, just wanted to italicize that. Anyways, we have 13i minus, 13i, which we have here, and then plus 11i squared. 11i squared is negative 11, right, because I squared is negative 1. Denominator, we get 4i squared, right, so 4i squared is negative 4. Okay, so if you write this in a plus bi form, you do, well, technically you do 13i divided by negative 4, which is negative 13 over 4i, which I have on the right. But again, I'm going to write it in a plus bi form, so the imaginary part comes second. And then negative 11 over negative 4 is 11 over 4. Okay, so that'll be the answer to this question. 11 over 4 minus 13 over 4i. Alright, if you need these solutions, pause the video here. Otherwise, I will move on. But yeah, just resume when you're ready. Alright, here are the next few questions. So you're going to see a bunch of these questions, or these types of questions on the homework. Okay, so just FYI. Question 3 is root negative 36, so we can rewrite that as root negative 1 times 36. And then we have root 36 times square root of negative 1. As we know, square root of negative 1 is I. Right, so, and root 36 is equal to 6. Okay, so this would be 6i. Okay, for question 4, this is, yes, pretty much the same as 3. You can actually just write this as I root 3, right? As you'll notice, like, all you do is rewrite this as root 3, the other number, times square root of negative 1, and this will become root 3i. Okay, all right, root 3i. Okay, question 5, here we have root 63 minus square root of negative 7 times 7 plus square root of negative 9. Okay, so first thing I'm going to do is actually, I'm going to rewrite root 63 as, so root 63 is 9 times 7, right? So that can be written as 3 root 7, right? Because square root of 9 is 3. So this can be written as 3 root 7. This, I'm going to rewrite that as negative I root 7, right? To get rid of that negative sign in the middle. Or not in the middle, but under the radicand. Yeah, under the radical. Let me say, sorry. Yeah, negative I root 7. Then we have 7 plus square root of negative 9. So that'll be 7 plus 3i, right? Because this can be written as I root 9. Root 9 is 3, right? So we have 7 plus 3i. All right, next we're going to FOIL. Okay, so 3 root 7 times 7 is 21 root 7. And then I have 3 root 7 times 3i, which is 9i root 7, which I have here. And then I have negative I root 7 times 7, which is negative 7i root 7. And then lastly, I have negative I root 7 times positive 3i. So that becomes, I guess, yeah. Let me write that in, actually. So this will be negative, right? Because negative I root 7 times 3i is negative I squared times 3 times root 7. So we just have to multiply all those, right? Okay, so again, we get negative I root 7 times 3i. That gives us negative I times I, which is negative I squared. And then we still have that 3 times root 7, which is 3 root 7, which we have here. Okay. All right, anyways, so let me first combine 21 root 7. And then we have negative, I'm going to combine this part because this is a real part, right? Because negative I squared, that's going to be negative 1 3 root 7. And then I have let me keep that here. And then these parts, right? The middle parts. Okay. All right. So that becomes 21 root 7 plus 3 root 7, right? Because negative, negative, that becomes positive, so it would be 3 root 7. And then from there, I'm going to factor out an I from these two parts. So I get 9 root 7, and then minus 7 root 7. Okay. Okay, so therefore this becomes 21 root 7 plus 3 root 7, which is 24 root 7, which we have here. And then here we have 9 root 7 minus 7 root 7. So since it's the same, root 7, we can subtract. So we get 2 root 7. But I'll write the I over here. Make this clear. Okay, so final answer is going to be 24 root 7 plus 2 root 7i. Okay. All right, but yeah, that's the final answer for that. If you need these solutions, please pause the video here. Otherwise, there's one more note I wanted you to see that's on the worksheet that I didn't include in this part in the solutions. But yeah, just pause the video here if you need a copy, and then resume once you're ready. Okay, so yeah, this next thing I'm going to show you, this next note, is going to be regarding like square root of negative numbers. So this is a note from the textbook. Okay, so special care must be taken when performing calculations involving square roots of negative numbers. Although square root of a times square root of b is equal to square root of ab when a and b are positive, this is not true when both are negative. For example, square root of negative 2 times square root of negative 3 is equal to I root 2 times I root 3, which then becomes I squared root 6, and as we know, I squared is equal to negative 1, so this becomes negative root 6. But, right, if you, treated this as normal, as we did here, right, for these, square product of the square roots, you would get square root of negative 2 times negative 3, which is square root of 6, right? But these are not the same, right? So this first way is, that we just did in the examples, this is the correct way. Okay, so in other words, when multiplying radicals of negative numbers, express them first in the form I root r, where r is greater than 0, to avoid possible errors of this type, which is what we did earlier in the example. All right, just a heads up for a mistake that you want to watch out for. Okay. All right, but yeah, I'll be ending the video here. If you want to copy this, pause the video here. But other than that, I hope you're all doing well today, and I'll see you all tomorrow. All right, take care and have a great rest of the day. Sorry, just gotta stop recording. All right, for real, have a great rest of the day. Bye-bye.